Welcome to CSE 168, UCSD's course on Computer Graphics 2 Rendering. In this course, we will be designing systems and writing programs for modern 3D image synthesis. In particular, you will develop a state-of-the-art path tracer with multiple importance sampling. We will be developing the theory in terms of mathematical aspects and algorithms underlying modern physically based rendering. I want to emphasize that this course is not about the specifics of a particular rendering package like PBRT or Mitsuba. However, we do optionally encourage you to use real-time ray tracing in optics, which is a real-time ray tracing API for NVIDIA GPUs. I want to say a little bit about myself. My name is Ravi Ramamurthy. I received my PhD from Stanford University in 2002. My advisor was Pat Hanrahan, who just received the Turing Award, computer science's equivalent of the Nobel Prize, in 2020. Over the course of my PhD thesis, I developed a technique known as spherical harmonic lighting, which is today widely used in games, example the Halo series, as well as in movies, starting with the movie Avatar, and in a number of other applications in graphics and vision. After graduating, I spent 6.5 years at Columbia University and then moved to the University of California, Berkeley. While there, I developed a technique known as Monte Carlo denoising, which has in many ways inspired the ray and path tracing revolution in industry, enabling very low sample counts and physically based rendering to be used for both offline and real-time rendering. I've been at the University of California, San Diego, or UCSD, since July 2014. I am the director of the UC San Diego Center for Visual Computing. I've been fortunate to receive many awards from my research, including the Presidential Early Career Award for Scientists and Engineers from the White House in 2008, the ACM SIGGRAPH Significant New Researcher Award in 2007, induction as an ACM Fellow in 2018, and induction into the SIGGRAPH Academy in 2019. If you're interested in a somewhat dated summary of my research, I put the link below, which goes to the video for my Significant New Researcher Award. I earlier taught CSE 167X, the Computer Graphics Online Massive Open Online course, which was twice recognized with an edX Prize certificate as being a finalist for one of the top courses on edX. CSE 168 is a follow-on from CSE 167. You need to have completed CSE 167 or the equivalent and done very well and enjoyed that course in order to have fun with CSE 168. Let me give you a very brief overview of computer graphics rendering. I acknowledge that these images are taken from the Bible of computer graphics, the text by Foley, Van Dam, Feiner and Hughes. And the slide ideas are courtesy of Mark Leboy in this slide. In the 1960s, the challenge in computer graphics rendering was how to solve the visibility or hidden surface or hidden line problem. That is, how do you figure out which objects are in front of which other objects, which objects occlude other objects? This led to some very clever algorithms in the 1960s and 1970s on hidden line and hidden surface removal. Sutherland in 1974, one of the pioneers of computer graphics, the first winner of the Turing Award in computer science for contributions in computer graphics, introduced in 1974 this taxonomy of visibility algorithms where he described them in terms of sorting. Now, if you don't attempt to remove the hidden lines, then you get something like this, where you can't really tell what object is in front of what other object. With hidden line removal, now you can clearly see that the box and the teapot is in front of the wall. And we can do some simple shading. So shade the individual facets or triangles on the objects and create the first step towards a nice computer graphics rendering like this. But obviously you would not be that interested in this course if this is all the quality of images we were able to produce. In the 1980s and 90s, interest in computer graphics shifted towards global illumination. The idea being that you want to model all the ways in which light can bounce around the scene, and global lighting on objects where light comes not just directly from the light sources, but bounces from the light sources off the walls, other surfaces in the scene, and then hits another object. Turner-Whitted introduced ray tracing. It has been 40 years now since the ray tracing algorithm was introduced, a real landmark in computer graphics that we build on heavily in this course. Researchers at Cornell introduced the Radiosity method, which is a different finite element method for simulating light transport, which for decades gave some of the most beautiful images in computer graphics. In 1986, Jim Kajia, then at the California Institute of Technology, introduced the rendering equation and path tracing, which formed the basis for what this course is about in terms of both the theory and the practical algorithms. This is a modern course developing a modern rendering algorithm based on the rendering equation. Here is the original image from ray tracing. You can see that by today's standards, it's very simple. But way back in 1979, 1980, it was a real landmark in image synthesis where you could see refraction of this checkerboard pattern through the sphere, the glass sphere, and you can see the reflections of objects and refractions. In fact, bitted ray tracing develops a recursive ray tracing method to get recursive reflections and refractions. Here is the Radiosity algorithm in the famous Cornell box, which is usually a box with a red and blue wall. And you can see color bleeding from the box. The red color on the wall can bleed onto the smaller yellow boxes, and the blue color from the right wall can also bleed onto the box, leading to a blue color. This captures the effect of diffuse or Lambertian interreflections or global illumination from one wall onto the surfaces of other objects in the scene. Kajia's rendering equation introduced this beautiful scene where you have caustics of the glass balls, where all of the color on the objects is really from the caustics, from global illumination, from reflections of the base polygon. Note that this captures all of the modes of light transport, including what one would typically get by radiosity or ray tracing algorithms, and caustics, which are very difficult to simulate, and simulates all of them within a path tracing framework. Why do we study computer graphics rendering? There are numerous applications for computer graphics physically based rendering nowadays, in movies, in games, in digital advertising. Most advertisements you see for products are rendered nowadays rather than photographs. In lighting simulation for architectural walkthroughs to see how the lighting in a new building would look, creating completely realistic digital humans, and within the general area of virtual reality. Beyond that, computer graphics rendering involves fundamental intellectual challenges. Can we create a photorealistic virtual world? That is, a virtual world where the visual effects appear as if they were real photographs, corresponding to the light a camera would actually capture in the scene. Can we understand the physics and computation of light transport? Physically based rendering has replaced the earlier ad hoc approaches in industry. From about 2011, offline rendering in the movies switched completely from earlier rasterization and more ad hoc types of approaches to physically based rendering. There are numerous courses nowadays at SIGGRAPH on the path tracing revolution in industry. In real-time rendering, since about 2018, NVIDIA has released RTX graphics processing units that achieve real-time ray tracing coupled with NVIDIA's optics software. You don't need to have an RTX chip to use optics. It will still produce very fast ray tracing, and this has enabled even interactive applications like games to routinely include ray tracing within them. In short, this beautiful imagery from realistic computer graphics has really revolutionized the way in which we see the display of images on our computer screens. And this is really a landmark in so many ways. We now have computer-generated movies, we now have real-time ray tracing in games, and in 2020, the ACM, which is the leading computer science organization, gave its highest award, the Turing Award, named for Alan Turing, pioneer in computer science, and widely regarded as the equivalent of the Nobel Prize in computer science, to Pat Hanrahan, my PhD advisor, and Ed Catmull, primarily for their role in developing computer graphics imagery for the movie industry and in other applications of computer graphics. Here are some examples of the ray tracer assignment from a local course in 2007, where you can see the very nice use of spheres and triangles, simple primitives with reflections and refractions to create these beautiful images. I gave the path tracer as an assignment at UC Berkeley a decade ago in a course, CS294. These are images produced by Daniel Ritchie and Lita Cho, which include the effects of complex image-based lighting or environment maps, reflective surfaces, volumetric surfaces, and create these beautiful images which showcase the power of physically based rendering. In CSE 168, for many years, there was the idea of a rendering competition. Can you model and render a physical scene? Can you develop the rendering technology required to do that? Here is an example again from the 2007 CSE 168 context with this beautiful butterfly scene where you're also modeling the reflections of the droplets of water, the scattering of light in the droplets of water, depth of field effects in the foliage, producing a very highly realistic computer-generated image. Over the course of CSE 168, we will develop a full path tracer with multiple importance sampling that will enable you to create images like this.